Welcome. Today is lecture 50, and so this week we are going to discuss about some of the microwave fundamentals for devices. If you have noticed, we have covered most of the important devices that are used in RF electronics so far in the course, starting with two terminal diodes and then compound semiconductor based transistors. We also talked about bipolar devices, gallium nitride, wide bandgap RF devices, and LDMOS, CMOS, etc. So now the last 2 weeks are actually on discussing about many other things that are very critical to appreciating these device applications. Okay. So when I say we are going to talk about microwave fundamentals for devices, microwave fundamentals are essentially microwave fundamentals, but there is nothing like for devices, but we will try to keep the focus on devices, the relationship of these properties or concepts with respect to devices. Okay. But many of these things are actually better covered or learned in a proper microwave engineering or a circuit design course. So you are also encouraged to maybe go through some of the basic microwave engineering courses in order to appreciate this better. Okay. So over to the whiteboard now. So what we are going to do this week is basically, for those of you who have already some background on microwave fundamental, it will be like a recap, and for those of you who do not have this background, it will be like a very basic, extremely basic treatment of the concepts that are required for appreciating the devices that we have discussed so far. So if you look at these images, these are from our group's research for at IISc, for instance, a single transistor, this last image that you see here is of a single RF transistor on wafer. Okay. So it is on the semiconductor wafer, and as I told you, this is the layout that looks peculiar like this is because you have a ground pad, and then this is a signal. This could be, for instance, the gate, this could be a signal which is the drain. Okay. So this is the drain and this is the gate, and these grounds are essentially sources. Okay. Now this is the configuration in which you actually make RF devices on the wafer. Okay. So you have to characterize them on wafer using this kind of a structure. At the heart of this is basically there are two fingers. So this is one gate finger and this is one gate finger, and the width of the gate finger is this periphery. You can see that could be, say, for instance, 100 micron. So you have total gate width of 200 micron. There are two fingers. This is your source pad, this is your source pad, and this is your drain. So this source is essentially connected to the bigger pad there, this source is connected to the bigger pad there, and then this gate will be connected here and the drain will be connected there, correct. So this is like the GSG configuration. Now why am I showing you this, or why am I talking about this, is because at the heart of it we are talking about RF signal, which are electromagnetic signals, and we are making them propagate in a semiconductor substrate inside all these metal structures or inside the semiconductor substrate itself. We are making them propagate in a semiconductor wafer. Okay. So what we have to talk about are things like transmission lines, okay, transmission lines or waveguides. Okay. We have to talk about these things because the electromagnetic wave, which is the RF signal, is going to propagate through these structures. So we call this particular structure GSG as coplanar CPW, coplanar waveguide, although purely from the electromagnetic point of view we do not do any elaborate design or simulation to come up with this structure like that. This is only for one wafer characterization. So although we call it CPW, it is not the real simulated or designed CPW, it is just to enable a measurement on wafer. So we call it a coplanar waveguide. It is sort of a waveguide, but in a real application, when you want to actually design a system and you have devices there, when you have proper transmission lines, then you have to design them very, very carefully. You need specific softwares to design the electromagnetic simulations of the transmission line or waveguides, and in that case we can call them as a strip line or CPW, etc. But here these structures are essentially for enabling on wafer measurements only. Okay. Now the electromagnetic waves essentially this is the signal which is the gate maybe, and this is the signal which is the drain. So your input signal is coming here and the output signal is going out from here. This is the drain, right, it is amplified also, correct, and these are the ground. To understand many of these things, it has to be we have to go back to the basics and appreciate the fact that an electromagnetic wave is an oscillating electric and magnetic, there are two fields, electric and magnetic fields, that are oscillating perpendicular to each other, but there are different modes, there are different ways in which they move. We do not have to understand the physics of all of this, but so far is whatever is necessary for appreciating the devices is something that we need to go through. So what are we going to talk about in this particular week? We are going to talk about basics of transmission line theory, and again, as I said, this is well covered in many microwave engineering courses that are available. Things like voltage wave standing ratio, the reflection coefficient, the Smith chart. We will go through these concepts in a very basic or elementary manner, so that you can appreciate the device and how they are actually used in a circuit better. Okay. But if you do not have an understanding of this so far, then it is really encouraged that you have to take a microwave engineering course, because here it will be quite brief. Okay. So, we are going to talk about transmission line theory, because the gate and the drain and the source, everything, they basically are like you are feeding them through transmission line. So, we need to understand transmission line. Okay. We are going to talk about waveguides and modes of wave propagation, but again this is very brief. Then the very important thing is microwave network, specifically 2-port network. We have various matrices to actually characterize them, and this is a little bit of mathematical, but we have no option, we cannot avoid them. We will talk about why we need these different kind of matrices. We have different kind of metrics that will enable you mathematically to understand and operate on this microwave network, because a transistor is at the heart of it. It's a microwave network, it's a 2-port network. When I say port, it's a connection of two, you can say, terminals. So, there is always a signal and there is always a ground in a way. You can assume that it to be like that. So, essentially it is a port. So, a signal, so for instance this is your gate and this is your source. So, a signal is coming in this. Okay. So, this is your input port. Okay. It is not like the signal is only coming here and this is grounded, it will come and it will go back. It is like the both of them will reinforce each other, but phenomenologically you can say there is one of them is source, one of them is grounded, one of them is bringing the signal. So, this is a port. Similarly, on the output side there is drain and then there is source. So, the output is with respect to the source between drain and the source. So, it is a 2-port network. So, transistor, a 3-terminal device, is a 2-port network. Okay. So, we have to understand how to characterize them, understand the properties in matrix, and then we will talk about impedance matching, which is a very important concept specifically for designing amplifiers. You need to match the impedance. What it means is that, we will come to that, is that your output, for instance, the output of your transistor may have a complex, for instance some A plus JB, and you have to transfer maximum power to the load. So, you have to match the impedance of the load and things like that. And finally, we will talk about passives, and that could be also a little bit detailed. Passives are very important, because on the wafer you need to fabricate, characterize, model and enable these passives oftentimes, such as in MMIC. MMIC is a complete RF chip on wafer on the same die monolithically. There is no separate integration of a discrete part, everything is fabricated on the same chip. Okay. So, in that case, for instance, passives are very critical. Even otherwise passives could be very critical. You are going to make not only inductor, capacitor, resistor, but also their transmission lines. You can make different other microwave components also. There are bond pads, there are wires, die attached. There are so many passives that we have to talk about, the via holes. Okay. So, these are passives that are enabled on the wafer, which we are also going to talk about. Okay. So, now I will keep the discussion more or less brief, so that our focus on the devices is not lost, but nevertheless we have to foray into the domain of microwave engineering for this week. Okay. So, what is basic transmission line theory? Whatever we talk about in circuit in our typical engineering classes, you have a lumped element. You have a capacitor, for instance, and it is a lumped element, which means it is a physically there is a capacitance. You buy it from the market, you can put it on the breadboard or the circuit, and that is how a capacitor, you know how a capacitor looks like. So, you put that, it is a lumped element. It works okay for analog low frequency signals, DC, etc., but even digital, for instance, where but the problem is when you have RF signals, your frequency, or you can say the wavelength of the RF signal is quite low, small. So, it approaches the dimension, the physical dimension of a capacitor or an inductor or a resistor. So, this lumped element treatment is no longer valid, because the value, the magnitude of the current or the voltage and the phase of the current or the voltage can keep changing at different points on the line. On a single capacitor, for instance, you have a single capacitor, the magnitude and the phase of the electromagnetic wave or the RF wave can actually vary with respect to time, with respect to position. So, it makes it very complicated. That is why you have to take the help of distributed parameter network, where you do not discretize them in a lumped element, you kind of treat it as a distributed overall parameter. So, a transmission line is basically, as I said, there are two lines, there is a signal and there is a ground. In a qualitatively you can think of that like that, and we say that this is an incremental length delta Z. So, what we are going to say is that we are trying to derive the expression or understand something called a characteristic impedance Z0 for this transmission line. So, this transmission line could be like two metallic lines, for instance, one metallic line on the top, one on the bottom. It could be many other configuration. It's a transmission line. Okay, so on a semiconductor wafer, you are going to need these metallic lines, with a ground plane. So this is a transmission line, and the transmission line has a characteristic impedance, which means that is the impedance of the transmission line. Okay, how do you find that out? For that, we have to take help of certain things. R is the resistance per unit length, L is the inductance per unit length, G is the conductance per unit length, and C is the capacitance per unit length of the transmission line of this particular segment delta Z. Now, if you multiply them with delta Z, then you get the total resistance, total inductance, total conductance, and total capacitance. You can see that inductance and resistance are in series, the conductance and capacitance are in parallel, as they should be. Now, if this is your 0 point and this is your delta Z point, then if this is 0 and that is your delta Z, so essentially at any point, if you talk about any point Z, then at the end of it you are talking about Z plus delta Z, it's like incremental distance that you are looking at. Okay. So now this particular incremental length delta Z is treated as a lumped element, and we are going to do the circuit analysis around that, and then the equations will tell us the distributed nature of the characteristic impedance here. Okay. So now you have to just solve the basic Kirchhoff's equation, Kirchhoff's current law, Kirchhoff's voltage law. How do you do that? So for instance, you can look at the voltage. So the variation of the voltage with respect to distance, and this has a unit of essentially, so this is R is the resistance per unit length. So R into I is basically voltage per unit length, which is what this unit is. So when you apply Kirchhoff's current law and voltage law around this discrete incremental the distance of the line delta Z, you get something like that. So you have a voltage drop that is dropping here, you have a voltage drop that is dropping here, correct, and that is the change from this point to this point, that is the voltage that is changed. Okay. So that is basically represented by this and this. Okay. Similarly, you are feeding in some current here, some of the current goes here and some of the current goes here. That is precisely what is happening. So this is the current that is varying, some of the current goes in the conductance, and some of the current goes in the capacitance. That is what is happening. The negative sign is because of course looking at the direction of the current and things like that. So these are called the telegrapher's equation, and you have to solve them simultaneously, okay, which I am not going to do. And if you solve them simultaneously, what you get is that you can actually express the voltage and the current as a function of an exponential parameter e to the power minus, this is a small gamma by the way, gamma Z, and something plus e to the power plus gamma Z. So here what is happening is, like, you can recall any in your undergrad, in your high school also, you talk about this minus e to the power minus kx plus e to the power kx for A1 or A2. There are two components here, essentially one of them like is a propagating mode, one of them is an evanescent mode where it can die out. So there are two components here. So there is e to the power minus and there is e to the power plus. V naught plus refers to the voltage wave that is incident on the whatever load you are talking about or the line, and V naught minus is the voltage wave that is reflected. Because it is an electromagnetic wave, there is always going to be something incident, and then there is always going to be something that is bouncing back. Of course, that will transmit also on the other side. Now similarly, current, you have impedance, the incident current I naught plus, and then there is a reflected current I naught minus. Okay, and this equations tell you as the voltage and the current as a function of Z, or the position on the transmission line. Now what is gamma? The small gamma? The small gamma is a propagation constant. In a wave equation you have the exponent factor, no? So it has this gamma has a unit of per centimeter per length. So this propagation constant, it tells you about the wave, essentially how the wave is propagating, and it has a real part alpha and an imaginary part beta. This beta is like the wave vector, you can say. It is like the 2 pi by lambda, where lambda is the wavelength of the RF or the electromagnetic wave that is propagating. So beta is like the wave vector, you can say. Okay. So this alpha plus j beta can be expressed by this. Again you see R, L, G, C, these are the discrete components of that particular delta Z segment, the lumped element. Of course you can simplify, make it I looking like that. The characteristic impedance Z naught is now given by R plus j omega L divided by the propagation constant. This is your characteristic impedance, and it can be expressed as this, which looks a little bit scary, but again, if your line is lossless, when you say the line is lossless, it means your resistor and your conductor is 0. The real part basically has to become 0. That is the definition of being lossless. If the line is lossless, if it is a lossless transmission line, then this characteristic impedance reduces to L by C, square root of L by C, that is it, because this part will go away, correct. So square root of L by C, where L is the per unit inductance, C is the per unit capacitance of the line, then you know the characteristic impedance of the line. Okay, then you know the characteristic impedance of the line. This is the phase velocity. Of course, the way you define characteristic impedance is also the incident voltage divided by the incident current, or the reflected voltage divided by the reflected current, okay, with the appropriate plus or minus sign. So, this is the characteristic impedance of the transmission line. This is what I told you about. You know, it is a lossless transmission line, and in that case you can express beta as omega of into square root of LC. Okay, that is all fine so far. Anyways, these are all mathematical manipulations, so I will just skip them again. Now, if you have, for instance, a coaxial line, which means there is a conductor in the center and then around it there is another line here. You know, it is like coaxial, there are two axis essentially. Okay, if you have a coaxial line with the inner diameter or radius A and the outer radius B, or you have a two wire line. So, there is one line here, one conductor here, two conductors. I always told you, right, there are two conductors. There is a parallel plate, one plate here, one plate here, the separation is D. In each of this situation, you can find out theoretically, for instance, what is the capacitance of that. It is a high school math. If you have two conductors, okay, there are two conductors that look like this cylindrically, then what would be the capacitance per unit length? This is the capacitance per unit length, this is the inductance per unit length. This is pretty much high school physics, by the way. So, you can actually derive the using the Gauss's law, the charge, the voltage, etc., and you can derive the capacitance. So, this is the unit resistance, this is the unit conductance. So, if you know all of these, then you can quickly find out, for instance, for a coaxial cable which is lossless, imagine this is lossless, what would be the characteristic impedance? Characteristic impedance would be, I told you, square root of L by C. So, this divided by this square root of this, that would be your characteristic impedance. Okay. So, just to give you a feel, if there is a lossless perfect, you know, two wire parallel plate line, etc., then you can derive the characteristic impedance. Again, the reason we are talking about all of this is because although coaxial cable may not be used on wafer, but it is good to know. The thing is, our transistors and all our RF components are lying on the semiconductor substrate. We are bringing the RF signal in and we are taking the RF signal out using transmission line on the semiconductor substrate. That is why it is very important to understand the concepts of characteristic impedance, for instance, of a transmission line. Okay, there are different kinds of transmission line. There is not, these are different kinds of transmission line: two wire line, parallel plate, coaxial, hollow cable, you know, things like that. Now, suppose I define this is a transmission line. You can see that this is a transmission line, and suppose I define this is the 0. Okay, this is the 0, and I am looking at a length from on the left side this way, and the length is L, any distance length is L. At 0 I have a load, the load is ZL, that is the load impedance across which you are delivering power, for instance. Okay, the current that is going is IL. Okay, so this characteristic, this transmission line is lossless, suppose lossless, and so the characteristic impedance Z0 you can define square root of L by C, beta, you know, the propagation constant, which is also like a wave vector. Now, how are we going to do the analysis around this transmission line which is terminated with a load of ZL? So, the ZL, the load ZL can be defined by the ratio of the voltage at this point by the current at that point, and at this point I have defined as 0. So, the voltage at point 0, the current as point 0, which is precisely this. So, that is your this is your load, the load, you know, the load impedance. Now, voltage, if I have an incoming wave of V0 plus and an outgoing wave or the reflected wave of V0 minus, then I have to add them together because the voltages are adding up. However, if I look at the current, okay, the current, for that you have to subtract out because you are talking about a potential difference. So, there is a voltage that is coming V0 plus, there is a voltage that is going out V0 minus, the difference of the two divided by the Z0, which is the characteristic impedance of the line, V0 plus minus V0 minus divided by Z0, which is the characteristic impedance of the line. This gives you actually the current that is flowing. So, this current has to divide this voltage, and that is why you get a expression like that. So, maybe I can remove the annotation here. So, that gives you a expression like this here, okay, this expression that you get here. And now I can do some algebraic manipulation and I can find out that the reflected voltage wave is a function of the incident voltage wave. This function is basically ZL minus Z0 divided by ZL plus Z0, very important. The load impedance minus the line impedance, the characteristic line impedance, divided by the load impedance plus the characteristic line impedance. This times the incident voltage wave gives you the reflected voltage wave. Okay. And a very important parameter that is very, very important when we actually characterize transistors for power, for instance, is gamma, and this is a capital gamma, this is not small gamma. This gamma is basically the reflection coefficient. The reflection coefficient is how much of the voltage is reflected back, which is V naught minus, divided by how much was being sent, incident. So, the reflected wave divided by the incident wave is the reflection coefficient, and that if you with this manipulation of the algebraic manipulation here comes out precisely to be this quantity ZL minus Z naught, ZL plus Z naught. So, what does it mean? If your ZL is equal to Z naught, assume that your load impedance is exactly equal to your line characteristic impedance, then your gamma will be equal to 0, right. That means there is no reflected voltage wave, okay, and the reflection coefficient is therefore 0. In many cases this is the situation that is desirable, which means you do not want a reflected wave, you want everything that you are sending in to be completely delivered to the load without reflecting back anything. So, if you have a reflection coefficient of 0, it means your load impedance is perfectly matched. It is perfectly matched to the characteristic line impedance, alright, that is what it means, okay, that is what it means. So, you want to basically come to a load, you want to get to a load which is matched to the characteristic impedance of the line. In that case your reflection coefficient will be 0, which is what you want, okay. Again these are mathematical manipulation, you can express the voltage and the current as a function of, instead of gamma now you have beta, because your alpha is 0, it is a lossless line, no. So, that is why you have the expression like that. You can express it as a function of gamma also, that is what it means, it can express it as a function of gamma also, okay, fine. Now, there are certain terminologies we just have to keep in mind. For instance, return loss is minus 20 log of reflection coefficient. So, if your reflection coefficient, again the reflection coefficient is never, you try to bring it to 0, but it may not be necessarily 0, okay. So, depending on the reflection coefficient that you have, you can define a return loss, you want the return loss to be as low as possible, okay. Now, again if you do some algebraic manipulation on the equations above, you see that the magnitude of the voltage magnitude on the transmission line. So, you have a transmission line, at any point the voltage magnitude in a function of Z can actually oscillate, because you see there is a theta and then there is a BL, okay. Beta is the propagation constant or the wave vector, you can say. L is the length of the line, okay, the length of the transmission line you are talking about. So, in a way you can say that the voltage wave that is going in has a oscillation, and there is a maximum magnitude and there is a minimum magnitude of the voltage wave, okay. There is a maximum and a minimum magnitude of the voltage wave that is propagating. So, the maximum magnitude is given by V naught plus this into 1 plus gamma, and this is 1 minus gamma. So, the ratio of the maximum voltage peak that you get to the minimum voltage peak that you get is called standing wave ratio, sometimes it is called also VSWR, voltage standing wave ratio. Essentially you are building a standing wave with a maximum voltage peak and a minimum voltage peak, and the ratio of both of them is the voltage standing wave ratio. It is a very important concept. You might recall that we have talked about VSWR briefly in our discussion on some of the data sheets in gallium nitride transistor. So, anyways, VSWR is basically 1 plus gamma by 1 minus gamma. So, this is a reflection coefficient, okay. Now, if your reflection coefficient was 0, in the previous slide I told you, if it is a perfectly matched load, then your reflection coefficient is going to be 0, which is generally the desirable case, you want a reflection to be 0, okay. So, if your reflection coefficient is 0, which means this is 0 and this is 0, then your voltage standing wave ratio becomes 1. So, the voltage standing wave ratio cannot become less than 1. 1 is the lowest voltage wave standing wave ratio, which means your magnitude of the maximum and minimum voltage is 0. What is mean physically is that there is no reflected wave, and okay, that is the voltage standing wave ratio. It can be large, by the way, it can be very large. The maximum value it can take is infinity. Infinity is the most horrible value, you do not, then it is a crazy situation. You do not want the VSWR ratio to be very high, or in other words you can say, when you test the ruggedness of a RF transistor, ruggedness, if you recall from our long back discussion on LDMOS and gallium nitride transistor, ruggedness of a transistor is the ability of the RF transistor to experience and still work fine against voltage excursions. So, that is related to VSWR. For instance, if your reflection coefficient is 0.5, which means 50% of the wave is reflected back, not a very good situation, but anyways, then it is 1 plus 0.5 divided by 1 minus 0.5, that is 1.5 by 0.5, that is 3. So, your VSWR ratio is 3:1, or you can say. In a way you are talking about the reflected wave being 50% of that of the incident. I mean the incident and you are basically getting 50% of the wave is reflected back, that corresponds to a VSWR of 1:3. So if you intentionally design a load such that the transistor, when you couple the transistor to the load, 50% of the wave gets reflected back. Suppose you are doing it by design, by intention, and you test the device, the performance, and if it is still performing okay, when I say okay, within a certain limit of tolerance, within a certain spec, if the device is still performing okay, you can say the device performs okay up to a voltage standing wave ratio of 3:1. Typically bipolar devices are tested in this kind of thing, because bipolar devices cannot go to very high voltage standing wave ratio. Many transistors such as LDMOS, gallium nitride HEMS can actually go to much higher. People even had test to 10:1. 10:1 would be crazy, right? So if you say 10:1, then this is 10 will be equal to 1 plus gamma, 1 minus gamma. You can find out how much gamma would be. It would be very significant fraction of gamma would be reflected. Okay, significant. So you are basically putting a very mismatched load. When a significant fraction of gamma, you can say when the gamma is very low or when the gamma is very high. When I say high, the gamma cannot exceed 1. A value of gamma equal to 1 means that VSWR is infinity. If a gamma is equal to 1, that means 100% of your wave is reflected back, which is the worst case situation. But even if gamma is suppose 0.8 or 0.7, that means 80% or 70% of the wave is reflecting back. That is a lot of wave that is reflecting back. Now that is a highly mismatched load. A perfectly matched load is where gamma equal to 0. When you have a highly mismatched load and you are keeping the transistor against a highly mismatched load, okay, then your VSWR is high. Suppose 10:1 or 8:1 is your VSWR, and you are qualifying the ruggedness of the device against that VSWR, which means you are qualifying the device against such a highly mismatched load. So in a nutshell, the ruggedness of the device that we talked about is actually this, which is how much of a mismatched load can your RF transistor handle. Okay, that is what basically it was, and so this all boils down to VSWR. That is why I was talking about VSWR. It is a very important concept in your microwave engineering. Okay, fine. And the distance between a maxima and a minima is of course lambda by 4. Distance between successive maxima or minima is lambda by 2. Okay, so that is pretty much basic. Now you can actually derive gamma reflection coefficient as a function of L. What is L? L is the position on the line, on any point L on the line, and you can see that this basically corresponds to this kind of expression like that. This all comes from the algebraic manipulation. So it is a gamma at 0, remember 0 is this point, at 0 point, okay, at the load. So gamma at 0 into e to the power minus 2 j b L. L is the length that you are looking at, b is of course propagation constant. So now if I say there is a length L, so I have a transmission line, okay, this is my 0 point, and of course there is a load here maybe at 0 ZL, but I am looking at this side and suppose I have a length of transmission line which is L. So at this transmission, at end of this transmission line L, if I look from this side, what is the impedance that I see? That is called input impedance. This is not the characteristic impedance of the line Z0. Please remember that Z0 is the characteristic impedance. Zin is the impedance of the line that I am seeing looking from here at the end of the line L. Okay. So if I do that, then basically this is because I am coming from 0 and I am coming L here. So I am putting it V of minus L. That means what is the voltage at this point and what is the current at that point, minus L minus L. So if I use this expression here and I do some more manipulation, then it looks like this. Okay, and I can simplify it and write it as this. Now this looks a little bit mathematically, maybe a little bit scary, but it's nothing actually scary. I'll come to that. So this is the expression for the input impedance looking into the line. Now of course I'm not asking you to remember or memorize anything here, but we have to appreciate certain constants. For instance, suppose what I do is that I take the eraser here and I remove this part. Okay, why did I remove that part? I removed that part because I want to say that suppose this is a short circuit, I have no load, I removed the load and I made it a short circuit, correct, at the load. If I have a short circuit, it means my ZL is 0, okay, the load is 0. If ZL is 0, then this quantity is gone, this quantity is also gone. What I have is JZ0 tan of beta L divided by Z naught, and there is a Z naught here. Z naught goes. So, I have J times Z naught into tan of beta L. This is the characteristic impedance of a transmission line which is ending at a short circuit. Can you see that? It is actually amazing, you know. So, this is imaginary of course, but this is it is a purely imaginary component. This is an impedance looking into the line if a short circuit load is there. Now, you have seen that this is a tan of beta L, which means it is very interesting because it is now periodic. Tan function is periodic. So, you have a periodically varying the input impedance can periodically vary as a function of L. Okay. What I mean is that this precisely this. So, the input impedance actually can vary. If I plot the input impedance with respect to Z naught, because Z naught, you know, normalizing with Z naught, then it is a periodically varying function in L. Okay. And what happens if the length of the line is suppose lambda by 2. So, I have a certain wavelength lambda of the RF wave that is coming. Think of it as a spot frequency, which means there is a single frequency of RF wave. I am not talking about broadband. Then suppose lambda is the wavelength of the RF signal, then lambda by 2 is suppose the length of the line. Okay, the length of the line is lambda by 2. Then your input impedance will be J into Z naught tan of beta is 2 pi by lambda, L is lambda by 2. So, lambda gone, 2 gone. So, it is J of Z naught tan of pi. What is tan of pi? Right? Look up your trigonometric table, you will find out what is tan of pi. It is sine of 180 degree by cos of 180 degree, correct? Anyways, so what I am saying is that if your length of the line is either lambda by 2 or for instance it is lambda by 4, you are going to get a very unique sort of a impedance. What is that? Is that if you have lambda by 2, as I told you, you will have tan of, you will have just J Z naught into tan of pi. Okay. If you take the magnitude of that, essentially it comes out to be ZL. Okay. No, that is even for a specific, you do not have to necessarily short circuit. This was a short circuit case. This was a case which was short circuit, and in that case the impedance comes out to be that, you know, the input impedance looking into the line comes out to be that. Suppose I do not have a short, even if I do not have a short, if I write this expression like that, you know, the original expression of the input impedance is something like that. If I put L equal to lambda by 2, then I will see that the input impedance is equal to ZL, which means if I have a transmission line like that, the impedance that I see from here is exactly equal to the load impedance for a length of the line which is lambda by 2. So, lambda by 2 length of the line of the transmission line does not change the load impedance irrespective of the characteristic impedance. Z naught does not matter. For any Z naught, when you look into a transmission line whose length is lambda by 2, then the input impedance is exactly equal to the load impedance. Similarly, if the length of the line is lambda by 4, if this length of the line is lambda by 4, we call it a quarter wave transformer. Any transmission line with a length of lambda by 4, okay, is called quarter wave transformer because it transforms the load impedance inversely. What I mean is that the input impedance looking from this side, the input impedance looking from that side is equal to Z naught square by ZL. Z naught is the characteristic impedance of the line square divided by ZL. ZL is the load impedance. So, that means when I am looking from the input side of the line, I see an impedance of Z naught square by ZL. In a way, the load impedance is mapped inversely. So, that is why it is called a quarter wave transformer, this segment of this transmission line which is lambda by 4. Okay. So, this is a very important and a very interesting property of the transmission line. You can use transmission lines of certain lengths to transform the impedance. Okay. For example, a half wavelength line will not change the impedance, whereas a quarter wavelength length of the line will transform the load impedance inversely. So, that means the length of the transmission line is a very interesting engineering tool that you have in microwave circuit design. Okay. So, with that we will conclude today's lecture. We basically introduced transmission line. There is a lot more of course, but we are going to talk about waveguides and other properties of microwave engineering concepts in the subsequent lecture. So, thank you for your time. I will see you in lecture 51.